Hello everyone, I'm Ela Bursalı and today I will explain topic 1.2, which is the nuclear atom and the atomic model. So this topic is again fundamental to chemistry because everything we study, such as bonding, reactions, periodic trends, the periodic table, is based on the structure of the atom. So firstly, the atomic model. To understand the nuclear atom, we must first understand the atomic theory developed over time. Early scientists like John Dalton, as you can see, proposed that matter was made up of tiny, indivisible particles called atoms. So this is what Dalton proposed. He said that atoms are very tiny and indivisible. However, Dalton believed that atoms had no internal structure, so this means that he believed that atoms didn't have subatomic particles. So his theory was then developed, and it was assumed by J.G. Thomson that there were electrons in an atom, and he proposed the plum pudding theory, which is this one, as you can see right here. So the yellow ones are electrons because they are negatively charged, and the positive one is the positive part of the atom, which was explained in this proposal. So this model by J.G. Thomson was disproven by Ernest Rutherford's gold foil experiment. So in Rutherford's experiment, alpha particles were directed at a thin sheet of gold foil, and most particles passed straight through, but a small number were deflected at large angles. So if alpha particles are deflected through a tin foil, and some of them go like this with a great angle and some of them go straight, Rutherford said that most of the atom has an empty space because it just goes through the space. So for the alpha particles that went through this tiny foil, he said that he concluded that the atom is made up of an empty space. Another conclusion he had was that there is a small, dense, positively charged center because these alpha particles are positive. And if there is a positively charged center, then positive and positive, they repel each other. So the alpha particles will deflect with large angles. So this was his another conclusion. And lastly, he said that the center contains most of the atom's mass because, as I said, he proposed that the center was positively charged and the other parts are empty. So he concluded that the center contained most of the atom's mass. So this developments of the nuclear model led to the modern one, which is, as you can see, composed of these subatomic particles. So according to the nuclear model, an atom contains of a tiny dense nucleus at the center, surrounded by electrons moving in the space around it. So this is the nucleus, and it contains neutrons and protons. The protons and neutrons together are called nucleons. And electrons, as you can see right here, are found on the outside of the nucleus, and they have a negative charge. So the electrons are in an orbital, as you can see, and they are negatively charged in contrast with protons and the nucleus, or the nucleon. So to talk about in detail about the subatomic particles, the first ones are protons. So protons are have a charge of +1, and their relative mass is 1. they are located in the nucleus, as I explained and as you can see here, and they determine the identity of an element. So in the periodic table, the periodicity is about, like, the repeating pattern is about the atomic number, which is the proton number of an atom. So the number of protons determines an atom's characteristics, and the identity of that atom. A neutron has a charge of 0 because it's neuter. And it has a relative mass of 1. It's located in the nucleus, in the center. And it contributes to the mass and the nuclear stability of an atom. And lastly, electrons. They have a charge of -1. Their relative mass is approximately 1 divided by 1836, and they're located outside of the nucleus in an orbit, as you can see right here, and they are responsible for chemical bonding and reactivity. So electrons are very important for an atom as well, because without electrons, chemical bonds or reactivity would be impossible. To sum up, almost all the mass of an atom comes from protons and neutrons, because electrons have negligible mass, as you can see through the relative mass data I gave and explained. So now let's define two very important numbers. First one is the atomic number. The atomic number, okay, let's say for oxygen. Oxygen has an atomic number of 8, right? So you write it here, because oxygen has 8 protons. This is a symbol of the element. Oxygen's symbol is O, and the mass number should be written right here. So in this example, they have given us, they used aluminium. Aluminium's proton number, so atomic number, is 13. Because the ionic charge is 0, the electron number is also 13, which is normally written right here. So first you write the symbol. On the bottom left corner, you write the atomic number, which is 13. If it doesn't have an ionic charge, or the ionic charge is 0, the electron number will be the same as the proton number, which will be 13. This is the electron part. And the atomic mass will be written right here, which will be 27 on the top left of the atomic symbol. And because we said that almost all the mass of an atom comes from protons and neutrons, the atomic mass could be found by adding the proton number and the neutron number. So in this case, in this example for aluminium, we're given the atomic mass, the proton number, but the neutron number is missing. So the proton number is 13, atomic mass is 27, then the neutron number is 14. So this is how you distinguish atomic number and mass number of a particle. The elements are often written in nuclear notation. This is very important because we use periodic table, and in the periodic table it will be very hard to write all the elements' name in long. For example, magnesium, aluminium, oxygen. So we use a nuclear symbol notation. In this case, aluminium is L. For oxygen, it was O. Like that. Now for the next one, we will talk about ions. So atoms can gain or lose electrons to form ions. Therefore, we can define an ion as a charged particle. So in this previous example of aluminium, I said that let's assume that the ionic charge was 0. So the electron and the proton numbers would be same. However, if this atom gains or loses electrons, it will form an ion. So the ionic charge will not be 0. So there are two types of ions. The first one is a cation, which forms positive ions, and the atom loses electrons, so electrons are negatively charged. If we lose them, we will become positive because we lost the negative charged particles. The example here is that aluminium has 13 protons and 13 electrons when it's neutral, when the ionic charge is 0. However, if it loses 3 electrons, 3 plus, the electrons will be 10 because it lost 3 electrons. So 13 minus 3 equals 10. So another way to calculate this could be, let's say x to this, a to this, and y to this. X plus a always equals to y. So the electron number plus the ionic charge always equals to the proton number. So let's look at anions right now. An anion is a negatively charged ion, and it forms when an atom gains electrons. So electrons are negatively charged. If you gain electrons, you get more negative, so you become an anion. So your electron number increases. So let's look at this example of oxygen. Oxygen, normally when it was neutral, like when its ionic charge was 0, it had 8 electrons, but right now it gained 2 electrons. So oxygen, proton number, the ionic charge, 2 electrons gained. What could be the electron number? If you forget this formula, like x plus a equals to y, x was the electron number, y was the ionic charge, and a was the ionic charge, and y was the proton number. This is very easy. So a is minus 2, y is 8, so x is 10. If you forget this, just think logically and say that, okay, we gained 2 electrons. When the atom was neutral, we had 8. If we gain 2 electrons, then right now we have 10 electrons. This is more simple, but you can also use the formula as well. So lastly, let's come to isotopes. So isotopes are atoms of the same element that have the same number of protons but different number of neutrons. So this means that they have the same atomic number but different mass numbers. An example I could give to this could be carbon. So let's say carbon 12 and carbon 13. So it has the same atomic number. Its identity didn't change. It's still carbon. But its mass number is different. So its physical identity changed, but its chemical identity is definitely still the same. So carbon's atomic number is 6. It has 6 protons. However, its atomic mass is 12 in this one and 14 in this one. So for the first one, you could say that 12 minus 6 equals to 6. So it has 6 neutrons. However, in the second one, 14 minus 6 equals 8. So it has 8 neutrons. So both are carbon because they have 6 protons, as I said, but their masses are different because the number of neutrons are different. So to sum up, isotopes have very similar chemical properties because chemical behavior depends mainly on electrons, not neutrons. However, their physical properties, such as mass in this case, can differ. Also, an extra information, some isotopes are stable, however, others could be radioactive. And the last topic we will talk about is an HL topic. It's mass spectra and relative atomic mass as well. So let's explain it from this graph right here, this diagram. Okay, I explained isotopes because elements exist as mixtures of isotopes. So what I mean by this, that a chlorine or a chlorine atom, like there isn't only Cl35 or Cl37. Chlorine exists as mixtures of different isotopes of this atom. So the atomic mass on the periodic table is not a whole number, as you can see from these examples. These are not whole numbers because the elements exist as mixtures of isotopes. So these atomic masses are a weight average of the isotopes based on their relative abundances. So this is very important. For example, let's go from the chlorine example. Chlorine has an atomic mass of 35, but an isotope of chlorine has an atomic mass of 37. And the average atomic mass is about 35.5 in chlorine because the relative abundances of these are different. So the mass number times the relative abundance of this chlorine atom, and the mass number, which is 37, times the relative abundance of this chlorine ion will give us this. So the calculations are like this: 35 times A plus 37 times B minus A plus B gives us 35.5. It can also be expressed through this graph. So this is the abundance, mass divided by charge. So 69 times 60 plus 71 times 40 divided by the abundance, 60 plus 40, which is 100, gives us the answer for this atom, which is, as you can see right here, 69.80. So the last topic is mass spectrometer. So to determine the isotopic masses and abundances, scientists use mass spectrometry. A mass spectrometer works in several steps. First is the ionization, which is atoms are converted into positive ions, and then these positive ions are accelerated by an electric field, and then these ions pass through a magnetic field. So if I have to draw this, there is like this, an electric gun, and then accelerators, and then right here, magnetic field. So ions enter right here through these electron guns. They get ionized, they are converted into positive ions, and then through here they're accelerated, and then they are deflected by passing through a magnetic field. And then right here the ions are detected and measured. So the key idea is the amount of deflection is inversely proportional to the mass to charge ratio. So this means that the lighter ions are deflected more, heavier ions are deflected less, and ions with higher charge are deflected more. This mass spectrometer produces a mass spectrum, and in a mass spectrum, through this mass spectrum, we can form this graph, which I explained previously. The x-axis, mass to charge ratio, which is m to z, and then the y-axis shows the relative abundance. And each peak represents an isotope. The height of the peak shows how abundant that isotope is, and from this we can calculate the relative atomic mass.